Welcome everyone. Thanks for joining the Zoom on time. But I think compared to the attendance last week, we still have some students not joined yet. So we may use a few minutes to wait for them. Welcome everyone. I noticed that some of you still log in without your UTS account. So if you are late like next week's, to avoid unnecessary delay, and when I start the lecture, so please log in with your UTS account. In that way, you can just log in the Zoom directly. You don't need to wait in the waiting room. Before the lecture, I also want to encourage you guys to start the project ASAP. Please try to build your own team or join another team. I see some of you have already got the team and also already picked the project topic. That's really good. Others, please also do this ASAP because you need time to find your teammates and also to talk with them to pick a topic. So this takes time also. And some people ask how to like find teammates. Um, like I think there are different ways. One way is like for any either on-campus lab tutorials or the online tutorials, we will leave like half an hour or 45 minutes for you to have your own discussion. So you can use this time to know your classmates and find your teammates. Um, Another way is like in previous years. Oh, let me see. So, okay, in previous years, some students may use the discussion board on Canvas. I think, let me see. Yeah, you can find it on Canvas here. Some people may just post the advertisement here, saying like he's looking for a team or maybe interested in some topic. You can also use this. Just use your own way and try to do this as soon as possible. And now on the waiting room. Okay. Now I think we can start our lecture today. So today we will introduce some concepts in graph theories, and also we'll talk some contents about social networks. And next week we will introduce some graph models. So graph consists of a set of objects. Also, we call them nodes or vertices, and with certain pairs of these objects connected by links, we call edges. So graph is a mathematical model of network structure, which study the topology. So to mathematically represent a graph, and we use normally we use this kind of notation. So for a graph, we use the G to represent a graph, and it consists of a set of objects or vertices, and also the set of the links between them we call edges. So for example, in the simple graph on the left, as an example, so for the vertex set, it consists of 5 nodes, 1, 2, 3, 4, 5. And the edges include 1, 3, 2, 3, 3, 4, 3, 5, 4, 5. Then we can use this to represent a graph. Graph is a strong when we use language to describe networks. For example, just some simple examples here. You can use a graph to describe like the actor networks. For example, here, the nodes represent actors. And if they appear in the same movie, then there will be a edge between them. And also, graph can be used to describe the relationship network. For example, here, the node represents individual or person, and the edge represents the relationship between them. It can be like, for example, here, Peter and Mary, they are friends, and Mary and Tom, they are co-workers. Also, graph can be used to describe like the protein interactions. The edge, the node represents protein, and the edge represent the interaction between the proteins. And so graph can be this common language to describe networks. For these three different networks, if we use a graph to describe them topologically, they are the same. they can be described with the same graph. Like here, we have a graph of 4 vertices, 1, 2, 3, 4, and also 4 edges between them. It can represent these 3 networks. So by topology, we mean like we only care about who they are, who the nodes are, and who links to whom. So no matter how you draw them, like no matter what the layout of the graph is, we only care about the nodes and the relationship between them. For example, here we see 3 different layouts of a graph, but actually they are the same. We can see like 1, 2, 3. They like kind of form a triangle here, and 4 is connected to 2. So if you think you pull this node 4 to here, then it will be like this, the second graph. And for the third graph, we just put the fourth node inside the triangle. So they topologically, they are the same. So they can be described as the same graph. And to describe edges, we have different ways to define the edge. Like in the direction aspects, edge can be defined as directed edge, or we call it arc. And so that means the relationship between the 2 vertices, like A and B, there is a direction, or the relationship is symmetric. For example, A calls B, that means A started the call to B, or A gave a gift to B, then B receives a gift, or A is B's child. So we use A to B to represent this relationship. We call this directed edge. Undirected edge means like the relationship between the 2 nodes are mutual or symmetric. For example, A and B are siblings or friends, then A and B, there's no direction between them. They are just friends. Or A and B are co-authors. That means like they are the author for the book or paper. They are both authors. There's a relationship between them. So that is the undirected edge. There are also other attributes to describe the edge. Okay. One is the weight. The weight of an edge, we use W to describe to represent the weight of edge AB. So it can describe like, for example, the frequency of communication between 2 nodes, or the distance of the roads. That can have different weight. Or ranks, like the friendship between 2 users, it can be have the ranking like best friend or second best friend. Or type, like for the edge can have different types. For example, the relationship between 2 individuals can be like friends or relatives or co-workers. And also like self-edge, that is the edge that starts from a node and also connects to itself, because this kind of edge is a self-edge. And multi-graph, that means like between 2 nodes or 2 vertices, there are multiple edges, not just one edge. Multiple edges can exist between 2 nodes. We call it a multi-graph. So to classify graphs, we have different ways. One way is to consider the direction. We can classify graphs as undirected graphs and directed graphs. There's a question asking about after the lecture, there will be the 7:30 to 9 tutorial online. And like I said in last week, you are free to go to any online or offline labs. You don't need to let us know. Just join. It's fine. It doesn't matter like which one you are assigned. I think we have enough resource for you to join any session. Hope it's clear. Okay, let's back to the lecture. For undirected graphs, that means like the edge in the graphs are undirected. There's no direction. So inside this kind of graph, um, if there's the edge between A, B, that means like they are the same. For example, the friendship on Facebook, it is a undirected graph, or course network is also an undirected graph. And in directed graphs, the edges have directions. Um, if there's an edge from A to B, that means like A to B is in the edge set, but it doesn't mean like B to A is in edge unless there's a B to A in E. And so directed graphs are also very common. For example, in Twitter graph, the relationship is like one A follows B, but it doesn't mean like B will follow A also. So especially for like celebrities accounts, like many people follow them, like they may not follow you back. And also like in phone call network, there will be a direction, like someone start a phone call, someone receive a phone call. And also like in citation network, like a paper or a paper cite reference another paper as a direction. E is the set of edges. So remember in the first slide, we say to represent a graph, we use two sets like G equals V and E. V is the vertex set, E is the edge set. Is it clear? Thanks for the question. Yeah, if you have any questions, just yeah. Okay. Another way to classify graphs are depends on the weights. Um, in the unweighted graphs, the edge has no weight. Or we can say the weight is the same for any edge. For example, the friendship on Facebook, it just means like two users are friendship. Or like in citation network, it just means like a paper cites another paper. But in weighted graphs, the edges can have different weights. For example, in coarse network, the edge can represent like how many edges or how many like co-authorships they have, how many or how many papers they publish together. Or in your network, it can mean like how far away are these two sports, or like what's the travel time from one sport to another. Or in the communication network, it can the weight can be the frequency between the frequency of the communication between two nodes. And there are also other types of graphs, like self-edges graph. Uh, that is like in the graph, self-edges are allowed. We call this kind of graph self-edges graph. For example, in the protein graphs, the same type of protein can have interactions, but also like hyperlinks in a web page. A web page has a hyperlink to itself. And also, another kind is multi-graph, like we introduced in the graph. Multiple edges can appear between two nodes. For example, in communication network or collaboration network. And in the lecture notes, some slides are so there's one question is, are all directed graphs weighted and vice versa? No, it's not definitely, because it's just two different ways to categorize graph. So next I will introduce some examples. You can see the difference. One thing I want to remark is here, like in the lecture notes, some slides are marked OPT. That means like those content are just optional for your interests. You just know it. It's good. And these contents are not related to any assessment in our subject. That means like it's not related to any the assignment or the final exam. So here, I give you some examples. So you can see triple W, it is a directed aid, because the hyperlinks between the web pages, there is a direction. And also it's a multi-graph, because between two web pages, they can have different, they can have not just one links between them. And also a web page may have a self-edge to itself. So it is a self-edge graph. Next example is like Facebook friendships. So it is undirected, because like a friendship between two individuals, like this mutual relationship. So it's an undirected graph, and it can be an unweighted graph if you just mean like they have a relationship, they are friend. But also like that depends on like how you define what's your definition in your application. Like some may define the relationship between the friendship between two person can be like strong, or you can so it has weight, then it will be a weighted graph. Or you can define the friendships as like the communication frequency between them. So that depends on like how you define the graph and how you want to analyze this network. And for citation network, it is an unweighted graph, because like the citation relationship, it just means like one paper cites or references another paper. It is directed because like the citation has a direction, like and also it is acyclic. Acyclic means like there's no cycle in this network. We will introduce this later, but here, simply to say, it just means like, because in citation network we have the time sequence, like a paper cannot cite back or cite a paper that is published before it. They can only like go forward. So there's a like a direction. There's definitely no like a cycle in the network. Next example is collaboration network. Collaboration network is a undirected graph because the collaboration is a mutual relationship, and also there may be many collaborations between them. So it can be it's a multiple graph, or if you define the calculation times as weight, then it will be a weighted graph. A mobile phone calls network is directed, like we induced there is a direction. Also, it can also be like a multi-graph or weighted graph, depends on like how you define the edge. And for the protein interactions, it is an undirected graph. That just means the two kinds of proteins they have interactions. And also it is unweighted with self-interactions, because the same type of protein they can have self-interactions. These are just some examples for you to understand how you can classify graphs. So in network analysis and graph analysis, how to represent a graph is very basic, but also important, because if you want to do some analysis on the graph, you need to, or want to do some implementation, you want to like represent the graph first. So we will introduce two representative formats here. The first one is the adjacency list. There's one question here. In the networks you just mentioned, what would the objects be? Or example of objects? Are we talking about processes or users? So yeah, that depends on different networks. The objects can be different. Like for the W network, the object would be a web page. In the Facebook friendship network, then the object would be a user or individual. Citation networks, the object or the node, we say node or vertex is a paper. So in different networks and or graphs, the objects can be different. Is it clear? Okay, good. Yeah, let's back to the graph representation. So the first one is adjacency list. So for this format, we represent a graph with some lists. For each node, we will use a list to represent which contains the vertices that are adjacent to this vertex. For example, in this example graph, for vertex 2, we only record the outgoing edges here. You will see why. So for vertex 2, we have two outgoing edges, 2 to 4, 2 to 3. Then we record these edges for vertex 2. Then for vertex 3, and there is an edge from 3 to 2. So we put one edge here, and then 3 to 4. Then we put the edges here. So for vertex 4, we have the out edge from 4 to 5. As for vertex 4, for vertex 5, we have 5 to 1 and 5 to 2. That's the adjacent list for vertex 5. By listing these edges, then we describe the graph. All the edges have been put up here. So this is the first format. And for the adjacent lists, the advantage of this format is like it is very compact, because like we only this is compared with the next format, which is matrix. We'll introduce later. Because in this list, we only record all the edges, and it is compact and also friendly for the memory. So it is good for large sparse graphs because we only need to, for sparse graphs, the edges are less, so only record the edges is possible. But the disadvantage is like the data structure is a bit complex compared to matrix, so it is a bit hard to implement. And also it is slow to access particular edges, because like if you want to access an edge, you need to go through the adjacent list for vertex until you find it. And also it is hard to implement computation. Like you want to insert an edge, or you want to like delete an edge. It is a bit hard to implement because you need to maintain the list and also go through it, find it, insert it, or delete it. Another way to represent graph is adjacency matrix. So this is easier or simpler because we just use a matrix to describe the graph. So like for this same graph, we use a 5 to 5 matrix. Each column corresponding to a vertex, and also each column represents a vertex. So how we fill in the matrix? For the item AXY, if a node X has an edge to node Y, then we set the value as 1. For example, for vertex 2, we have edge from 2 to 4. Then we set this 2, 4, this value as 1. And also we have a edge from 2 to 3. Then we set this element as 1. But if X does not have an edge to Y, then we just set the value as 0. AXX, when X equals Y, that's the diagonal elements. Then unless the network has self-loops, then otherwise the value will just be 0. If there's self-loop, then we set the value as 1. And also, if the network is undirected, then that means like AX squared will be equals to AYX. In that sense, like we only need to like keep half of the matrix, we can represent a graph. So you can see the adjacency matrix, it is a very clear format. It is very obvious for you to see the graph. And also it is good for small graphs and dense graphs because for the small graphs, it is easier. The matrix is small and the values are less. It's possible for you to describe it or like save it. And also for dense graphs, the values are, you can really use the space, use the values. Also, it is easy to implement computation, like compared to the adjacency list. If you want to like access a value, you just, if you know the 2 endpoints, then you will just find like AXY, then you can find this edge. Also, it's easy to access and update the edges. And also, it is friendly for GPU speed up because like the matrix format aligns well with the memory architecture of the GPUs. And also GPU is good at matrix computation. But the disadvantage for the adjacency matrix is that it is hard to store the additional attributes of vertices and edges. You can, for the matrix, you can just maybe at most you can save if there is an edge, or maybe save the weight of the edge. But if there are other attributes, it's not easy to save this attributes. Also, it is space waste when the graph is sparse, because like in the matrix, a lot of the values will just be zero if it is a sparse graph. But in real world graphs, many networks are sparse. So in our research, when we are doing research, we barely use this matrix formula. We mainly use the list. Another reason is also like it cannot handle very large networks because the space to save the graph, especially for large graphs, it is not possible to save them in the memory. Next, so one thing we care about in graph theory is about the connection between nodes. So next we'll talk about paths and also connectivity. So a path is just a sequence of nodes, each consecutive pair linked by an edge. And the length of a path is just the number of edges in the path if it is an unweighted graph. But for weighted graph, the length of a path is just the sum of the weights of the edges. For example, here, let's see some paths, say from C to K, there are multiple paths. One is from C to G, G to E, E to I to K. In this path, there are one, two, three, four edges. So we say the length of this path is 4. Another path is from C to D, D to B, B to F, F to I to K. This path have 1, 2, 3, 4, 5 edges in this path. So we say the length of this path is 5. And also, of course, there is like another even longer edge. From longer path is from C to D, D to B, B to F, F to H, H to G to E to I, then to K. 1, 2, 3, 4, 5, 6, 7, 8. This is the longer path of 8. Just one thing to mention here is like this 13 nodes graph is actually a very famous graph. The name is ARPA network, which is the first public packet switch the computer network. Before it was telecommunication network. This is the first computer network, which is first used in 1969. So a particular important kind of non-simple path is a cycle. We already briefly mentioned before. So what is a cycle? A cycle is a path that has at least 3 edges, and also the first and the last nodes are the same, and other nodes are distinct. For example, inside this network, inside this graph, A to B to G to C to A, this is a cycle. It has more than 3 edges, and the first and the last nodes are the same. And from F to I, K, L, M, J, E, G, H, F, this is another cycle. If you like see carefully, actually in this ARPA network, every edge is belongs to a cycle. This is like specifically designed because for redundancy, like if any edge fails, the nodes can still like there's another way from one point to another point. They're still connected. Just it's designed like this. So Next, we talk about connectivity. Before let's see the question. One question here. With the unweighted graphs, would we be only looking on at the number of edges for the shortest path between two nodes? You guys see if they are directed or indirect. Yeah, we will talk about shortest path later. I will introduce the detailed definition about the shortest path. But here you just know the length of a path, that's the number of edges for unweighted graph. For weighted graph, that'll be the sum of the weights of the edges. But also like for shortest path, that is the shortest length of the path. So yeah, for unweighted graphs, we only count the number of edges on the path. But for weighted graph, we need to sum the weights of all the edges. Is it clear? Is it what you're asking? Okay, good. Thanks for the question. So now we talk about the connectivity. So in the graph, we say node A is connected to node B if there is a path from A to B. That's the node connectivity. For the graph connectivity, we say a graph is connected if any two nodes in the graph are connected. So one really important definition here is connected component, or component for short, of a graph. It is a subgraph where any two nodes are connected inside the connected component. Any two nodes are connected, and there's another property. It is maximal. So maximal, we will use this term in many definitions. So by maximal, that means like you cannot put or add any other vertex or edge into this graph, but the graph still maintains the property. That means for a connected component, it is already maximal. That means if you add any vertex or edge in the connected component, then it is not connected. That is the maximal subgraph that maintains this point. Let's see an example, still the same upper network. So we can see, obviously, any two nodes in this graph, they are connected with each other. You can now find any vertex. There's not a path between them. But what if we delete some edges? Say we delete F to I, G to E. Then we say, of course, like the whole graph is not a connected component because like from H to I, there is no path. But we say like these two separate paths, they two themselves are connected component because like any two, for example, for the left part, any two nodes here are connected. And also it is maximal because you cannot add any other node or edge to it and it's still connected. So the left part itself is a connected component and the right part itself is a connected component. If we keep deleting edges, the left part still it is connected. So it is still a connected component. The right side is the same. And if we keep deleting, then the right-hand side will separate into two connected components, the left one and the right one. So that's the connectivity. So another definition is called giant component. So we call if the largest component, like in a network, the largest component has a significant fraction of the graph, or it includes most of the nodes in the graph, then we call it a giant component. Like in this network, the component in the middle, it is a giant component because it contains most of the nodes in the graph. One interesting thing is like in real world graphs, if there is a giant component inside a network, then usually there will be only one giant component. So why this? Why do you think if there is one giant component, then there must be only, usually there is only one? Because like, let's suppose like inside this graph, there are two component, two giant, we say like there are two giant component. Then like if they both like contains many nodes, if just a single edge between any nodes between these two giant component, then it will be connected. So it will be combined as one giant component. This is very easy to happen if there are two giant components. So usually there is one giant component in the network if there's one. Next, we talk about the connectivity on directed graphs. So first, let's define two kinds of sets. So the outset of V given node V, the outset of V represents the set of vertices that V can reach. The inset of V, that is contains the vertices that can reach V, like what other nodes can reach V. Let's see an example here. So for node A, the outset of A is like this. You can see like A can go to D. So we have D here. A can go to B. B can go to C, to G, to F. Because A can go to B, that means like A can also go to CGF through B. So that are CGF. And of course, A can go to itself. And F can go to H. Then we have H here. So these are all the vertices that A can reach, which consists the outset of A. For the inset of A, we can see, so E can go to A. So we have E here. And also C can go to A. We see in edge here, C. And also B can go to C. G can go to C. That means B and G, they can all go to C. Yeah, of course, A is here. That's the inset of A. Next, we define the strongly connected component, SCC. Usually we say SCC in a directed graph. SCC is a set of nodes such that inside SCC, each pair of nodes can reach each other. That means out A equals to in A, like A can reach all the vertices here, and also all the vertices can reach A for any node A in S. And also it is maximal. That means like there's no subgraph, like any graph like contains this graph has this property. So for example, here, we have a few, like we have some SCCs here. The first one is this big SCC, ABCG. You can see like they can go to each other. Any two nodes, they can reach each other. And other four nodes themselves, they consist SCC because like they can only reach to themselves. Like for F, it can reach H, but H cannot reach to F. So these are the SCCs. But how can you compute a SCC graph in a directed graph? The easy way is just to to find the SCC that a node A belongs to, just intersect the outset and inset of A. For example, here, the subgraph in the blue shade is the outset of A, and the pink one is the inset of A. The intersection is this middle part. It's the SCC that A belongs to. Another concept is like directed acyclic graph, DAG, which is also important. It is a directed graph G, but without any cycles. That is called directed acyclic graph. That means like if X can reach Y, but Y cannot reach X because there's no cycle. For example, AC here is a DAG because C can reach A, but A cannot reach C. So this is the direct graph, but there's no cycle in it. So combine DAG and SCC. Actually, any directed graph can be expressed in terms of DAG and SCCs. Sorry. For example, here, in this graph, each subgraph in this cycle in this like circle is SCC. If we contract or if we see this each SCC as a single node, and then if there's one edge from a node in one SCC to another SCC, then we have an edge between these two SCC. Then this like abstracted graph is actually a DAG. You can see they have directions, but like they cannot reach each other. So if we see like this is node 1, node 2, node 3, node 4, node 5, then this abstracted graph with 5 vertices with edges between them, it is a DAG. This procedure is actually very useful if for some graph research problem like reachability, because it helps to decrease the size of the graph. If we like contract these SCCs, then the contracted graph will be much smaller. So next we talk about the shortest path. Oh, there's another question. Let's see. In the DAG part. So the question is, how the highlighted part is not a cycle in the because there's no cycle. Remember, like a cycle is a cycle is at least um pass with at least three edges, and also the first and the last vertex are the same. But like you cannot, for this specifically for this subgraph, you cannot find any cycle in it, right? That's why we call it a DAG. Another question is why E, D, F, H are also part of SCC? Are you referring to this slides? Refty? Sorry, I hope I pronounced your name correctly. Yeah, this slide. So this they don't belong to the same SCC. They are different. That means like in this graph, we have 1, 2, 3, 4, 5 SCCs. They belong to different SCC. This is one strongly connected component. This is another one. This is one. This is one. This is one. So they do not belong to, like in this graph, we can find 5 SCC. Is it clear? Rafty? Is it clear? If you still have any questions, please let me know. As long as a single vertex has direction, it can be classified as SCC. That depends. Like if like for this kind of vertex, it has outgoing edge. There's no incoming edge. So most possibly it is SCC itself, because like for SCC inside this SCC, each node has to reach each other. If there's no incoming edge, that means like no other edge can reach itself. Then the node itself, it is a SCC. Does it make sense? We also have, yeah, normally yes. We also have some practicing tutorials you can practice. You can try use this way to find SCC for any node. You can list these outsets and also insets, and then do an intersection. Then you will know what SCC it belongs to. Okay, great. Thanks for the questions. Now we talk about so that there's still more questions. One question is, does that mean like undirected graphs are SCC? Notice here, SCC is a definition on directed graphs. It is the definition on directed graphs. On undirected graphs, we just use connected component. And I don't know what you mean, like E is a whole network. It is just we are talking about finding SCC in a directed graph for E itself is a SCC. That's it. That question is, should they only be considered SCC if they have self edges? no, yeah, if you consider this, the definition here, I think it makes sense if you consider the definition here. SCC, oops, sorry. No, E can be a SCC. It is just a trivial SCC, only has one vertex. Okay. I think we're up to the shortest path. Thanks for all the questions. So given two nodes, the shortest path between them is the path that has the smallest length. But yeah, inside the graph, the shortest path between two vertices are not always unique. Let's see, like for example here, from vertex C to vertex K, there are two, like one shortest path is from C to B to F, F to I to K. This is length 4. 1, 2, 3, 4. But also C, if C goes to G to E to I to K, is also 4. So the shortest path may not be unique. So how do we find shortest path between two nodes? One simple way is just to use the breadth first search, or we call BFS. And we will talk mentioned many times in our subject. It is commonly used, and it's very effective. So like from node C, if we want to, we do a BFS on C. Firstly, we go to the first stop. We go to all the neighbors of C. That is to A, to B, to D, to G. So with distance of 1, we can reach all these vertices, or say the neighbors of C. And we continue from these neighbors, which we call neighbors. Neighbors neighbor. Like if we go from, but like not reported yet. If we go from like A to B, B has been reported, and so we don't need to record it. And then from B, we can go to D has already been reported, B to F. So we have B to F here, and then G to H, G to H, and G to E. So with distance 2, we can reach F, H, and E, and continue. If we continue from neighbor's neighbor, and then we go to the depth of 3, and then we have F to I, and also from H goes to F, already reported, and also E goes to I, and also goes to J. So with distance 3, we can go to I and J, and continue. We can distance 4, we can go to K, M, and distance 5, we can go to L. So the shortest path from C to K is 4, and we can go from C, B, F, I, K. So that is a simple way to compute the shortest path. But yeah, like someone asked, on weighted graphs, the shortest path, you need to consider the weights of the edge. For example, the two shortest paths on undirected graph, if we consider the edge, like for this path, the edge is this, so we can sum them up, like 2 plus 1 plus 3 plus 1, which is 7. And another path is 8. So we say the shortest path from C to K is this one. It is shorter than this one. And with the definition of shortest path, we can define the diameter of a graph. So the diameter of graph is defined as the length of the longest shortest path in the graph. That is like after you list all the possible shortest paths between all pairs of vertices, the max value will be the diameter of a graph. Of course, you don't need to like list these like very close vertices. You can list like this like more far away from each other, the vertices. Then you can when you list the paths and then you compute the length, like for example from A to L. From A to L, one path is from A to C to G. 1, 2, 3, 4, 5, 6. This is 6. But there's another way. It's like 1, 2, 3, 4, 5. So yeah, this is the tricky part. Like when you are listing, you need to make sure like you need to find the shortest path. So this is not the shortest path between A and L. This is 1. So this is length 5. So you just keep listing all the shortest paths until like keep checking. If you find the length of 6, then you delete 5, increase to 6. Yeah, until you find the largest value. That's the diameter of a graph. Another thing we care is how dense is a graph. That's the density of a graph. To define this density, let's give the another definition first. So the upper bound of edges that may exist in a simple graph, that is a graph like has no multi-edges. The up bound of edges in a simple graph which has n vertices. The Emax, which is the up bound of the edges, is n times n minus 1. That is on directed graph, because each node n can connect to the other n minus 1 nodes. For example, here. Sorry. For example, here, this directed graph has 4 nodes. Then the upper bound of edges are like each node connects to all other nodes. Oops. A the same, A to D, A to B, A to C. So in this graph, we have 4 times 3, which is 12 edges. But for undirected graph, since like there's no direction, so the number of the edges need to divide it by 2. That's the upper bound of edges that can exist in a simple graph. So the density is defined like this. E max is like we defined before. So then density of a graph G is the number of edges in this graph divided by E max. For example, in this upper network, we have 13 nodes. The E max is a undirected graph. So the E max will be 13 times 12 divided by 2, which is 78. And the number of edges, we have 17 edges. So the density of the edge is 17 divided by 78. That's the density of a graph. Also in graph theory, an important problem we study is called graph isomorphism. That's to detect if two graphs are the same topologically. So we define it like this. I've sorry. Isomorphism of graphs G and H is a bijection between the vertices of G and H. This bijection F such that for any vertex U and V in VG, if U and V are neighbors in G, then FU and FV are also neighbors in H. That means like if two graphs are isomorphic, they have a like one-to-one correspondence relationship between the vertices and also the edges. For example, here for this graph G and graph H1, so we can you can see if you can find this kind of bijection between them. Yes, so if we map vertex one, if we map vertex one to vertex B, and then we map vertex 3 to vertex C, vertex 2 to vertex A, vertex 4 to vertex D. Then we can check. You can see there's edge between 1, 2. It's not very clear. 1, 2. And for the mapped vertex B and A, there's also edge. And for edge 2 and 4, the corresponding edge is here, A to D. And for 1 to 3, the edge is B to C. And 3 to 4, 3 to 4 is like C to D, is this one. And 2 to 3 is mapped to this one, A to C. So there exists a bijection. Of course, the bijection may not be the unique, maybe different. Like you can also map like vertex 1 to vertex not B, but D, it also satisfies the definition. So we can say G and HI, they are isomorphic. But what about G and H2? Are they isomorphic? You can have a think. No, it's not. I think it's quite obvious because like if you may already notice this node C here. It has degree of 1, so it has only one edge. It cannot be mapped to any nodes in G because there's no node in G has vertex 1, has degree 1. Because the for the mapped nodes, the edges can also need to be mapped. So there is no bijection between G and H2, so they are not isomorphic. Oh, someone also commented in the chat. Thank you. Yeah, they are not isomorphic. Yeah. So actually, to identify the graph isomorphic is actually not easy because this is a more complicated example. Yeah, if the graph is more complicated or has more nodes or edges, if like here, this graph G and H, they are layouted like different. So if you don't check carefully, then actually they are isomorphic. So the bijection is like this. It's already marked in, so each mapped nodes, they have the same color. Like vertex A is mapped to vertex 1, and G is mapped to 5, like so on. So like for vertex A to 1, it has like 3 edges. A to I, it also has the edge to the 1 to 4, and A to H, then 1 to 2 is all the mapped vertices, and A to G is 1 to 5. So actually they are isomorphic. I'm sorry, I just noticed a question here. What are the numerical values on a weighted graph? Does that mean weight 5 is 5 times the weight, or weight 1, or necessarily? Not necessarily. What are the weights? No example. Yeah, so for the question is, what are the numerical values on a weighted graph? I hope you mean what you mean is like the value on the edge. So, because on weighted graph, the weight of the edge, that means like in different networks and also in different applications, it's up to the up to your definition. Like you can define like the communication, let's say on let's say in the phone call network, you can define weight 5 as like two users A, B, there are five calls between them. And then weight 1 means like there is only one call happen between two users. So in that way, you can say weight 5 is 5 times the weight of weight 1. So normally, yeah, that's how you define the weight. You want to give the weight some meaning, some relationship between them. Yeah, the example Delia gave about the distance between paths also makes sense. Yeah, it's a good example. Like, what's the distance between two spots? Like one is like 5 kilometers, one is like 1 kilometers. So the weight up to the user, how you define it. Hope it's clear. Okay, so your second question is isomorphism possible for weighted graphs? One-to-one correspondence between nodes, edge, and weights. Um, yeah, normally we consider graph isomorphism on weighted graphs, but if you consider the unweighted graphs, and that's also up to how you want to define the isomorphism. Like, the weight can be yeah, if you want a more strict definition, then the weight has also be the same. But if you want a loose definition, you may not consider the weight. That's up to you. Yeah, okay. So another question from Changling. What meaning about the right FA? Yeah. So this FA equals 1, that means that's the bijection. We use F to denote the bijection between the vertices. So FA equals to 1. That means like the vertex A in graph G is mapped to vertex 1 in graph H. Yeah. Yeah. Zero is correct. Thanks. Okay. Yeah. So graph isomorphism is widely used in many applications. So also like for example in chemistry or in bioinformatics, you want to compare if like two molecular structures are the same, and also like in graph research, like there are many other research problems are related to graph isomorphism. Another example is like subgraph isomorphism, which is more popular because in many real life applications, usually you will be given a smaller graph, like we call it a pattern or a motif. You want to find in the big graph or the dot graph if there is any subgraph in the data graph that is matched with this pattern, this given pattern. So this is called subgraph isomorphism. Yeah, this is for interest to give you a brief introduction. Uh, okay, so I guess we still have some time to introduce. We used last few minutes to introduce two other types of graphs. One is widely used bipartite graph. So bipartite graph is inside this graph, we have two groups of nodes. Like the example here, we have two groups of nodes. So the edges only appear between the two groups of nodes, not within the groups. We call this kind of graph is like bipartite graph. This is very common. For example, like we say, we have a set of individuals, and they also a set of events. The individuals, they attend different events. Like different people attend the same event, or a person may attend a few events. And another example is actors and movies. And the edges only appear among the actors if an actor appears in a movie. There's an edge between the actor and the movie. Another example is customers and items they purchase. The set, one set can be the customers, another set can be the items they purchase. Yeah, actually, also like the users and movie rates. These are actually from our project. You may already notice that, like in the movie recommendation, the POI recommendation, and also the last project about the maximum click, which is from Alibaba, the e-commerce data. So all the given datasets are bipartite graphs. Yeah, another example is authors and papers. Authors have authored a paper. Let's see. Yeah, another question. I think, Dahlia, your question is similar to what another question is. Like normally on unweighted graph, but on weighted graph you can define up to you if you want to more strict isomorphism definition or like a loose definition. Yeah, for strict you can define like the weight can also be the same. So the last type of graph is heterogeneous graph, which is inside the graph, the node and the edge types, they may have different types. This is more common in reality. Like in this example, in biology, in this graph, the nodes have different types, like can be DNA, RNA, or like drugs, disease, virus, and the edges also have different types. It is more complicated. So when you are go to like industrial, it is more common for you to find like these heterogeneous graphs. But for this subject, you just for you to know this graph, it's okay. All right, I think that's all the lecture for today. Oh, yeah, we haven't got to the social network part, which is about the strong and weak tests. Next week, we will continue to introduce this part. If you have any questions, you can let me know. Otherwise, then we will start the lab in 5 minutes.
Zubo, I have a question. Are you going to upload these Zoom recordings so we can reference back to them?
Yeah, actually, yeah, I already uploaded the week 2 recordings. You can find it in modules. Like week 2, I think you can find it here. Recordings of week 2 lecture.
Oh, okay, perfect. Thank you.
Yeah. Okay, thank you. Thanks everyone. Let's have a few minutes break, then we will start the tutorial, online tutorial.